Okay, this is AP Chemistry, Unit 1, Chapter 2. And we're still reviewing what we learned last year in Honors Chemistry. Okay, and we know what the law of conservation of matter, or mass, states, and we know that it was Antoine Lavoisier that is credited with the discovery of the law of conservation of mass. We watched a video on this last year it was the Einstein, the E equals MC squared video that we watched. Remember, he was the mass guy. And this law says that mass cannot be created or destroyed, can't magically appear or disappear, okay? And he also said that combustion involves oxygen. It requires oxygen as a reactant. Combustion requires oxygen as a reactant. So basically he says that your reactants, what you put in, have to equal your products, the amount that comes out, okay? It's not going to magically appear or disappear. The law of definite proportions is a very easy law. It's something that we already know. It means for any given compound, it will always contain exactly the same proportion of elements by mass. The same proportion of elements by mass. This simply means that H2O, that's a molecule of water, and it's always going to be 2 hydrogens and 1 oxygen, no matter what. Okay, it exists in those definite proportions. All right, the law of multiple proportions. Let me read to you the scientific definition, and then I'm going to break it down so that it makes more sense. Here's the scientific definition. When two elements form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. Okay, that doesn't make a whole lot of sense. But basically what it's saying is that two elements, let's go back to water. Those two elements, hydrogen and oxygen, are part of water. But hydrogen and oxygen can also make up other elements. That's hydrogen peroxide. It's just in different proportions. Okay? Same two elements, just in different proportions. All right, so basically we're saying the same elements can combine in different proportions to form different compounds. That's a whole lot easier to understand. Okay? That's the law of multiple proportions. All right, moving on. This is still part of early discoveries, early laws, early discoveries about the atom. We've heard of Dalton, John Dalton. Basically, he's the first to discuss the atom. As an entity, an individual entity. With the properties that it can combine with other atoms, and it can make compounds. So he was the first to really discuss the atom, and this was around 1808. So we're in the 1800s. Avogadro came along this early 1800s again, and we know who Avogadro is, but he tested gases, and we know that he knows that the same number of particles of any gas have the same volume. And remember, we talked about last year, we're talking about at STP, at standard temperature and pressure, that they all have a constant volume, and then that volume is 22.4 liters. Okay, 1 mole of any gas has a volume of 22.4 liters, and Avogadro was the one that came up with that. All right. Some early experiments dealing with the atom. We need to be aware that J.J. Thomson is the electron guy, and Ernest Rutherford is the nucleus guy, okay? Very important. J.J. Thomson did his experiment with this instrument called a cathode ray tube. And basically he just shot a beam of light, which is basically electrons, through this tube. And this tube had a positive end and a negative end. And he shot this beam of light through this tube, and he noticed that it would bend up towards the positive end of the tube. And what that showed is that these particles must be negatively charged, because we know that opposites attract. And that's why they were bending up towards that positive end of the tube, the positive end of the magnet. And so he was the first one to discover this particle that we now call the electron, then that it's negatively charged. Rutherford, his experiment is called the gold foil experiment. And basically what he did was he had a piece of gold foil, and he tried to shoot alpha particles at this piece of gold foil. And alpha particles are positively charged. And when he did this, he found basically two things. Most particles, most of those alpha particles passed through the foil, okay? But then he also noticed that some bounced back, okay? So if these are positive particles and most are passing on through, but then you have some that are coming back, well, if they're bouncing back, we know that like charges repel. So that this must be hitting some other positive particle. And they're passing through because we know most of an atom is empty space. So he discovered most of the atom is empty space, but there is this centrally located part of an atom that he called the nucleus that has a positive charge, which was causing the positive alpha particles to repel. All right? And that is Rutherford. And we know now, the modern view of the atom, we know about an atom. We know that it has electrons, which are located outside the nucleus and are negatively charged. And they orbit around in this electron cloud. And we learned last year about electron configuration and orbitals, and we'll get back into that much later. We also know that there are protons and neutrons in the nucleus. Protons are positive. Neutrons have no charge. These are both located in the nucleus. Okay. The positive proton equals the negative electron as far as charge goes. Those charges will counteract each other. The neutron has no charge, but the mass equals the mass of the proton. Okay? All right, as far as shorthand, a lot of times we'll see something like this written, okay? Whereas that K is the symbol, and we know K is potassium. This 39 is the mass, that's the larger number, and 19 is the atomic number, and that doesn't change for potassium no matter what. Atomic number is the element's identity. And mass is protons plus neutrons. Okay? So if we want to know, hold on. If we want to know how many neutrons, then we would simply take the mass minus the number of protons, and that will tell me the number of neutrons. Okay? We know that if this is a neutral atom, that the number of protons equals the number of electrons. So this particular potassium atom would also have 19 electrons. It can gain and lose electrons. The number of electrons can be different. That just is going to give it a charge. Potassium has one valence electron that it will lose, and it will become positively charged when it becomes an ion. We know that the mass number can change because the number of neutrons can change, and all that it does is affect the mass, but the number of protons can never change. All right. As far as chemical bonds go, we know that this is a force that holds atoms together. And they hold them together in compounds. Okay? We have covalent, which share electrons. Okay? And those are called molecules. Molecules are covalently bonded together. And then we have ionic compounds that transfer electrons. One atom is giving electrons away, the other one is taking them. So we have ionic compounds. And we need to remember that when atoms lose electrons, they become positive. Those are called cations. Remember that T looks like a positive sign. Okay? And when they gain electrons, they are negative, and those are called anions. And those two come together to form ionic compounds. All right, this should all be sounding familiar. Still nothing new. All right, on the periodic table, and this is just some basic periodic table stuff. We know all of this stuff already. Elements are classified by their properties, and they're arranged by increasing atomic number. We know that. We know that groups and families, that means the same thing. They run vertically, up and down. Group 1A, those are called the alkali metals. Group 2A, those are the alkaline earth metals. Group 7A, those are the halogens, that's the next to the last group. And group 8A, those are the noble gases. And remember, they're unique because their valence shell is already full. They don't like to bond. All right, and periods run horizontally, side to side, and there are 7 periods. And just some general information about metals and nonmetals. Remember, they're separated by that stair-step line on the periodic table. Most elements are metals. And remember, that little guy at the top of group 1A, hydrogen, he is not a metal. Even though he is in that area, he's not considered a metal. Don't forget that. Most elements are metals. They are good conductors. They lose electrons and become positive. Okay? They are malleable, which means we can beat them down into flat sheets. They're ductile, meaning we can form wire from them. They're shapeable. Okay? And gold is the most ductile of all the metals. Nonmetals are brittle. We cannot shape them. They'll break apart. They're brittle. They are poor conductors. They tend to gain electrons and become negative. All right, and the semi-metals or the metalloids, those touch that staircase, that stair-step line that separates the metals from the nonmetals. These touch the staircase. Except, remember, aluminum is an exception. Except for aluminum, he's a metal. All right, and these just have characteristics kind of in between metals and nonmetals. They're more metal mostly than nonmetal, so I say they're metallish. Okay? They're kind of in between the two. All right, and that is all for today. We will continue on with naming compounds tomorrow.